Hi ladies, and welcome to another snow day and a lesson about pedigrees. So at this point you should have already done the interactivity and watched the Amoeba Sisters video. So this is just a real cap up of a summary of what we've done so far, making sure we're all on the same point. Okay, so to define it, a pedigree is a family tree that traces the occurrence of a trait in a family. And this would be used to study the occurrence of a disease in a family and to identify the inheritance patterns. There's a couple of key features that I want you to note when you're drawing the pedigree that I think were a little bit emphasized in Amoeba Sisters, but just in case. So the first generation is going to get a Roman numeral 1, the next generation a Roman numeral 2, the third a Roman numeral 3, then after that we would do a Roman numeral of 4, whatnot. And notice that each generation is in a single line. Okay, that's a very straightforward line. We're not deviating from it. So if I were to add this person's family, for instance, like let's say she has a brother and their parents. Okay, notice when I drew it in, I made sure, and they're not the most beautiful squares and circles, but it's all in the same line, so I can tell that everyone here is in generation 1, everyone here is in generation 2. So make sure that when you're drawing your pedigrees, you're keeping it in a straight line. So just to go over a couple of symbols that some we've already talked about, but the others I think are new to you. So we know that a male is a square, a female is a circle. If you don't know the gender, or rather the sex of an individual, you can use this symbol. I've also seen a triangle used. This would be for like a fetus, for instance, where you know that someone's pregnant, but you don't know the sex of the individual. Affected is colored in, and it can be male and female. But twins, this is what fraternal twins would look like, and this is what identical twins would look like. Okay, just to show you how to do some more complicated symbols. Okay, ladies, so now we're getting into what geneticists really use pedigrees for, and that's determining the inheritance pattern of a disease or a trait that we're trying to trace. So a geneticist would look at the family history of a family and see who has this disease, how is it being passed on through the family, and that'll give some clue for future generations. So in this particular one, I'm going to look for evidence that allows me to draw my conclusion. Now this pedigree, you'll notice that there is someone in every single generation, generation 1, 2, 3, and 4, who has the disease. Okay, so that's your first tip-off about the inheritance pattern. The other clue that you have is every single person who has it has a parent who had it. Their parent had it, their parent had it, their parent had it. So when I see that everyone has, that the disease is present in every single generation, and when I see that everyone who has it has a parent who had it, I know that this is an autosomal dominant trait, meaning it's not sex-linked and it's a dominant trait. So now what we want to do is, I'm probably going to ask you next to give the genotypes of individuals in the family. Okay, so we're going to try to do 2 people from each generation, include at least one affected person and a parent. So let's start with these people right here. So that is the male person there. So looking at this, we know a little bit about their children. We know that they have a child who doesn't have it, a child who has it, a child who has it, a child who doesn't have it, a child who has it. Now we know that they don't have it. So because it's an autosomal dominant trait, this person has to be little a, little a. Now this person right here has 2 possibilities. They could be big A, little a, or they could be big A, big A. Right? But there's some clue that we have here, and that is this. Do you see that they have a daughter who doesn't have it? That means that this is not possible for this parent. That parent has to be big A, little a in order to have a child who's recessive. So there's 2 right there. Okay, if I were to do this girl, I know that she's little a, little a. This person right here, because I know that they had a parent who's little a, they would have to be big A, little a. This person, little a, little a. You get the gist of how this works. Okay, so we would just continue this down through the generations. I know that this individual has to be big A, little a, because they had a parent who didn't have it. This parent doesn't have it. This person has to be big A, little a. This one has to be little a, so forth and so on. So that's how we genotype autosomal dominant trait. You'll notice that in this particular pedigree, there are some clues to the inheritance pattern, and you can see that it's not present in every single generation, that it skips generations. So here we have one individual who has it, but parents who don't. That tells me right away that this is an autosomal recessive trait. Autosomal recessive trait. Okay, so if it's autosomal recessive, that means this person is little a, little a, little a, little a, little a, little a. So taking a look at this parent right here, let me erase that. So this parent right here, I know that they had a kiddo who's little a, so, but they don't have it themselves, so they must be big A, little a, big A, little a, because they had to pass on both little a's to their offspring. Now, no one here, none of these kids have the disease, and this person doesn't, so this individual could be big A, or they could be big A, little a. I'm not really given any clues to that, so I'm going to stick with my or there, as in there are two possibilities. Taking a look at the dad of this generation right here, because they have kids that have it, again, big A, little a, big A, little a. So this would be the pattern that you see with an autosomal recessive. The other big clue that you'll sometimes see with an autosomal recessive, and it's not in this pedigree, but sometimes you'll see an individual who has it and another individual who has it, and you'll notice that every single one of their kids has it. If you see this, and you're seeing that it's skipping generations, but that two people who have it only have kids who have it, again, big tip off that it's a recessive trait. Okay, ladies, so let's look at the inheritance pattern that we have here. So this is actually a real family tree. This would be the royal family. So this is the royal family of England, and over here we have the Russian royal family. And if you'll notice, the son here is affected, and this particular trait that we're tracing is hemophilia. The Tsarina, his mom, right here, always felt really guilty about having a son with hemophilia. She figured she carried the gene since her brother had it. And so she did all sorts of things like consult Rasputin, which turned out to be a really bad idea, which led to the Russian Revolution and the death of the Russian family, including Anastasia, sorry to say. But I digress. That's a history lesson. We're talking about genetics. So let's talk about genetics. You'll notice something different about this pedigree. You're seeing carriers, which you learned about in the Amoeba Sisters video. Carriers just means that they're heterozygous. Now, what's interesting about this particular pedigree, the clue and the evidence that you have here is the only people that are affected with this illness are males, which means this is a sex-linked recessive trait. So we have sex-linked recessive. Because it is sex-linked, we're going to need to use X's and Y's to designate genotypes. So here, Alexis would be right here, X, and he was going to have a little h for having hemophilia and a Y. And then we don't know, maybe Anastasia was, well, we know she didn't have hemophilia, so she could have been XH, big H, X little h, or she could have been X big H, X big H. So she has these two options there. We know that the mom, the Tsarina, she was X big H, X little h, because she ended up passing on that trait to her son. So again, you could go through and sort of identify what these are. Remember that when it's sex-linked, you're going to have to use X's and Y's. Okay, so I, of course, have to talk to you about how to draw a pedigree. And the best way I know how to do this is with a fictional pedigree, and that would be the trait of being a wizard, which J.K. Rowling actually followed genetic rules when she wrote the book. One more atta girl for J.K. Rowling. Okay, so let's try the Harry Potter family tree. So I'm going to start here with James Potter. We knew he was a wizard. And we have Lily Potter, who we knew was a wizard. And they had one son, Harry. Okay, according to the books, James was a pure blood wizard, which, of course, in genetics we would call homozygous. But Lily had a sister, right? And her sister was not a wizard, and they came from parents who were not wizards. So this would be what Lily's family looked like. Now, Lily is really the key for us figuring out what the trait of wizarding is, what inheritance pattern it holds. So I'm, of course, not done with my pedigree. I need to put Roman numerals for each one here. And then I need to have some sort of key. So I need to say, okay, this is wizarding. Okay, so if we look at Lily, Lily has it, but her parents do not, which means that it skips a generation, which means that this must be an autosomal recessive trait. Okay, and there you have it. A little fictitious family tree to practice doing pedigrees. Your next step is to go ahead onto your OneNote and do your pedigree homework.